As Nathan stated earlier, writing a vector-valued function r in terms of the arc length parameter always results in a norm of the first derivative of the vector-valued function with respect to s equal to 1. This is called unit speed. This normalizes the speed at which the function traverses the arc length. This is called unit speed. Now, if C is a smooth curve given by a vector-valued function, r of sub s, or r of s, where s is our arc length parameter, and the normalization of the first derivative will be 1 with respect to the vector-valued function r of s. Moreover, if t is any parameter such that this value equals 1, then t must be the arc length parameter. This may be intuitive by plugging in values of t for s. An appropriate substitution will be made, but if the normalization gives a value of 1, then t must be the arc length parameter by this theorem. Now, to define curvature, let's see let C be a smooth curve given by r of s. Where s is the arc length parameter as stated earlier. The curvature k at the point s is given by the equation that is the normalization of the tangent vector with respect to the arc length parameter, which is also given by the same function in a little bit different notation. Everything needs to be written in terms of the arc length parameter in terms of this to work. As an example, we will show that the curvature of a circle of a radius r is equal to 1 over r, which is the value of k. So my notation for a circle that has an equal sign. The parameterization of a circle is easily given by r cosine of t, r sine of t, first derivative with respect to r is negative r sine t, r cosine t. When we normalize this, it's quite easy to see that when you take a square root, the sine will become squared, the cosine will become squared. They both multiply by r. You can pull an r out. Sine squared of t plus cosine squared of t will give you a value of 1. So this will be equal to r squared, square root of that, which equals r. Therefore, s of t is equal to 0 to t of r du. You can pick any point. 0 is convenient. This will give you the arc length in terms of the parameterization of t with respect to the curve given by this value. Once we integrate, we find that s is equal to rt. S over r is equal to t. So, taking this, we plug in our unit speed back into the original equation. We reformulate this. So r in terms of t is now given by r cosine s over r plus, and then for the I component, the j component is given by r sine s over r, and I've ran out of room. I'm going to block that in. And so we take a normalization. Well, this should be with respect to s, but for this purpose, we'll get negative sine r is a constant in this equation, so we pull it out. T prime is then given by when we normalize this, this should be cosine. My bad. It's easy to verify that we get 1 over r. Thus, we have proved that the curvature of a circle of radius r given by its unit speed parameterization in terms of curvature is equal to 1 over the radius. For a new theorem, if C is a smooth curve given by a vector valued function, r of t, then the curvature at C or the curvature of the curve C at the point T is given by this equation. K, the curvature, is equal to the normalization of the first derivative of the tangent vector with respect to T divided by the normalization of r prime of T. This also equals r prime of T cross r double prime of T normalized over the normalization of r prime of T. This norm itself is cubed. This is a scalar value, this is a scalar value, this gives you a scalar value. The cross product of two vectors is a vector, but when normalized it is a scalar. For a quick example, we'll find the curvature of the given curve given by this vector value function. R prime of t is equal to this. The normalization is equal to R double prime of t is equal to this. R prime of t cross R double prime of t is equal to negative 4t squared plus 2t squared, negative 4t plus 0 times negative, so we make that a positive, and then 4 minus 0. When we normalize this, well, we can simplify this. This will just simply become negative 2t squared. That's still 4t. Just remove the positive sign, it's unnecessary. When we normalize this, well, we can just call that t prime of t, since that is the equivalent formulation to what we have found in the previous one. This is given by the equation 4t to the fourth plus 16t squared plus 16. Square the components and add them together and then normalize them. We can take out a 2, and then we're left with t to the fourth plus 4t squared plus 4. Once again, we see the same pattern from earlier. This is equal to 2 over t squared plus 2. K sub t is given by what we have found earlier, t prime of t. It's normalization divided by the normalization of r prime of t cubed, which is given by 2t squared plus 2 over t squared plus 2 cubed. As we can see, this is equal to 2 t squared plus 2 squared at any point on the curve. Given by at any point t on the curve. Another theorem. If c is the graph of a twice differentiable function, given by y is a function of x, then the curvature at xy, or a point xy, is given by the following equation. The proof of this is pretty nasty, but it does rely much on the same concept from the previous iteration of this as a vector value function. Simply the z components will be 0, being simplified dramatically in this case. It is also equal to the acceleration at a point minus the normal vector at that point, those two vectors subtracted from each other, divided by the speed squared. Or the normalization of this. Well, yes, technically that's true. If we wanted to prove this, hopefully I have room. R of t will be a function of t, f of t. 0, we have parameterized f of x in terms of t, and we have parameterized x as t. You can say let x equal t to verify this. However, I'm not going to write it out. It's superfluous. R prime of t is therefore 1, and then f prime of t, the first derivative. Look familiar? As I said before, the 0 components, or the z component, the k component, is 0 for these cases. R double prime of t is also now going to be this, double prime of t, 0. So now, if we cross these two vectors, that is my shorthand notation, a little abusive notation. We'll see that we get 0, 0, 0, and then we get f prime of t, or f double prime of t, I should say. So if we take the normalization of this, this is my shorthand notation, we will get f double prime of t, the absolute value, which is exactly what we have found here since y is a function of x. This makes the proof true. Now, if we go here and we take the normalization of r prime of t, this will equal 1 plus f prime of t squared, all under the radical. Now, if we normalize this, then it's very easy to see that, or we are given what we need. Now, the proof will be complete once we write everything out. F double prime of t over, and remember we have to cube this from the formula from earlier, 1 plus f prime of t squared cubed. This will give you the 3/2 that we see up here. Everything checks. QED. Now, we have a new thing called a circle of curvature. Let C be a curve with a curvature K at a point P. The circle passing through the point P with radius given by the formula from earlier, centered on the concave side of the curve. Sharing a common tangent with P. Our tangent line is a circle of curvature. Is the COC. Ha ha. Its radius is called the radius of curvature, shorthand, and its center is called the center of curvature. These things are somewhat unnecessary to even talk about. But as a quick example, we will go over it. find the radius and find the curvature and ROC of the plane curve given by this x equals 0. Y prime is given by 3 e to the 3x. Y double prime is 9 e to the 3x. Now, if we cross these two, it's, well, there's almost no need to cross these two because we're given the other formula. And we're only working in 2 dimensions. So k of x is given by y double prime if we plug in the point 0, it's easy to see that we get 9. Oh, we got 10 cubed. And then r sub k at 0 is equal to 1 over the curvature, which equals 10 to 3/2 over 9. Last theorem. If r of t is the vector valued function for a smooth, or a position vector valued function for a smooth curve C, is my position vector shorthand. Then the acceleration vector is given by where k is the curvature, and ds dt is the speed. We'll prove this thusly. These are from known formulas that we memorized. Times the normal vector. It is quite easy to see that we have what we are trying to prove. Which is what we desire from up here. R prime gives you the speed, or the velocity. And it is important to note that k is given by the normalization of t prime over r prime of t normalized. I'm not going to write that out. We will do one example, and then we are free to go. prime of t is given by 2t squared, negative t squared I should say, when I normalize this. Four plus 4t squared plus t to the fourth. Looks familiar? We found this earlier. T squared plus 2 equals ds dt. Nice, we have found one component that we're looking for. K is therefore given by this value. Take derivative, we get 2t from here for at component. We have found k, we have ds dt. We need an, which is given by the curvature times ds over dt squared. This is from earlier. We took this, so we're simply using the value that we found in the other example, since this is essentially the same example. Now, doing this, we'll have 2t squared plus 2 squared times t squared plus 2 squared. So a sub n equals 2. We have found the components we're looking for. Therefore, we are done. Thank you very much. And have a good one.